Hi everyone, I'm Membuat. Today I'm going to discuss how we can utilize antennas in order to detect tumors in breast cells. The concept is very simple. Imagine if we place a breast tissue between two antennas, and these two antennas act as sensors. We can basically characterize any biological tissue in terms of electrical features such as permittivity and tangent loss. Basically, biological breast tissue is highly non-homogeneous material. It's a mixture of blood, fat, and many other biological components having different permittivity and tangent losses. But effectively and locally, we can model this entire breast tissue by using a single permittivity and tangent loss, which is basically a homogeneous modeling at a particular frequency. Due to the presence of the tumor cell, that homogeneity of the breast tissue will be hampered. And this change or this variation of the electrical material property of the breast tissue will be captured into the transmission coefficient or S21 plot. So the bottom line is the signal propagation from antenna 1 to antenna 2 will be impacted due to the presence of the tumor cell inside the breast tissue. Since this is a two-port network, we can definitely model this entire system by using a scattering matrix or S matrix. Because we have 2 ports, we'll have 4 elements in this S matrix. And we'll be concerned mostly with the transmission coefficient, which is basically S21 or S12 in this case. And if we plot the transmission coefficient versus frequency, then we might have different responses depending on the tumor size. Tumor location will also change the S21 plot. So by having these multiple simulation plots, we can establish a correlationship between the transmission coefficient with the tumor cell size and tumor cell location as well. So this is a very simple concept. By using 2 antennas, you can also employ multiple antennas around the breast cells in order to detect the tumor cell more precisely. And that could be done by using a circular array of antennas as well. But for this discussion, I'm keeping it simple. I'm only designing 2 antennas and a breast phantom between them. Now, in order to define or in order to design this entire system in EM software or electromagnetic software, we definitely need electrical material property for the biological tissues. And this is our 3-layered breast tissue model or phantom. You can see there are different layers: skin, fat, and fibroglandular tissue, which is basically the dense tissues inside the breast. And it also determines the density of the breast tissues as well. And the tumor tissue is the big sphere in the center. And this is the table that I'm using to characterize this entire biological tissue in terms of its electromagnetic CAD model. Please remember that this is a single frequency data, so you cannot utilize this data for different frequency. And this is only valid for 33 GHz. And I took this data from a journal paper published in IEEE MTT journal or Microwave Theory and Technique journal. Now let's move on to the design part. I will design this entire project in HFSS from the very scratch. So let's move on to the HFSS interface now. Once you open ANSYS Electronics desktop, you will see this user interface. And from there, you'll have to click this HFSS in order to start an HFSS project. And this will launch the HFSS interface. So from there, you will have to create a substrate first. Let's name substrate 1. And the material is Rogers. So just type Rogers and it will pop up 5880. And let's change the dimension of the substrate. We'll use variables in order to denote all the dimensions so that we can entirely parameterize this project. So SL by 2 minus SW by 2, 0. SL is the length of the substrate, which is 4.7 millimeter, SW is as well 4.7 millimeter. And along the x-axis, we'll have to define the length, and along y-axis to define the width of the substrate. And along z, the thickness will be denoted as SH, which is 0.508 millimeter. So this is our substrate. Now we are ready to define the ground plane on this back side of the substrate. Let's define ground. Ground 1. Let's change the color because it's a metal, just to differentiate between the substrate and the ground plane layer. Let us also parameterize this ground plane. SL by 2 minus SW by 2, 0. SL, SW. Okay. Now let us create the patch on the top of this substrate. So in order to do that, let's transfer the coordinate system from the back side to the top side. And you can precisely control the transformation from this coordinate system. So it should be 0, 0, SH. Okay. And you can name it like patch center CS. And this is our patch. And let's denote the length as PL. So PW by 2, the width. So the patch length is 2.75 millimeter and patch width is 3.11 millimeter. X is PL, Y size is PW. And we can change the color and also the name, patch 1. Okay. All right. Now let's create the microstrip line. So microstrip, this coordinate system, this should be PL by 2. This is our microstrip. Let's name microstrip 1. Let's change the color as well and the dimension as well. So this should be 0. Along the x-axis, the length of the microstrip line is SL by 2 minus PL by 2. And then along y-axis, we are going to define the width of the microstrip line. So it should be MW by 2. Okay. So the width of the microstrip line is MW and it is 0.2 millimeter. All right. Okay. Now let us create the inset feed for impedance matching. And it should be MW by 2. This is our inset. Let's name inset 1. And along the x-axis, the length of the inset is defined. So let's define a new variable for that, INL, which is 0.2 millimeter. So millimeter is already there. And along y-axis, we're going to define the width of the inset. So inset in W, which is 0.15 millimeter. we can just simply copy this thing, the first inset, and create another inset on the other side. So to do that, just select this microstrip, coordinate system, and then select this one, go to edit, duplicate, and mirror, and select this as the center point for copying or mirroring. And then you can see you can rotate it around this axis, and just simply press Y from the keyboard, and then you can see that the rotation is only confined along the y-axis. So from the keyboard, just press Y and then click. All right. Now select patch and select these two insets and go to subtract menu. Make sure the tool parts are inset 1, these two insets, and the blank parts should be the patch, and press OK. All right, now we created everything. Now we have to define the port. Let's define a port offset. We can name this coordinate as port CS, and this should be SL by 2 minus PL by 2. We also need to change the coordinate system plane because the port must lie on the YZ plane. So we have to change it to YZ plane. So anything you will draw will be drawn on the YZ plane now. Okay. So this is our port. Let's define the dimensions. So along x-axis, it should be 0. Along y-axis, it should be, let's say, 0.15 times or millimeter. And this one should be then 3 millimeter. And along the negative z-axis, it should be minus sh and 2. Okay, and you can change the color, red. All right. Since we're going to define a wave port, and in HFSS, if you want to keep the wave port inside the radiation boundary, you need to define the PC cap on the back of the wave port. A PC cap is just a metal boundary condition that is imposed on the backside of this wave port so that it can be placed inside a radiation boundary. So simply create a rectangular break on the backside of the port. Let's name it PC cap. It should be PC material. PC, yeah, this one or this one, both are fine, anything. All right, now let's define the dimension as minus 1.53. X should be actually the thickness of this brick is 0.2 millimeter. SH, and it should be 2 times SH. Let's reduce the thickness to 1.1. Okay, fine. And we can change the color just to differentiate it from the rest of the structure. And this should be wave port. So wave port, let's rename it wave port. All right. So the rest of the ground, microstrip, and patch, they are basically metal or PEC boundary. So just simply select perfect E or perfect electric conductor for them. Then we have to define a port here. you can hide the PEC for the time being, just to reveal the port from here. Now, to define a port on this boundary, I mean this red color surface, just select it and go to assign excitation and wave port, and define an integration line that shows the voltage direction. This is from negative. Make sure you have this triangular dot. This is selected right on the middle of this ground plane. That's why the pointer has changed to triangle. So it denotes the middle or the center point of any edge. Anyway, so from here to here, the top of the microstrip line. And then you're going to define for 50 ohm impedance. So this was our first port. Now you can show all of the structures. Okay. Now let's assume the second antenna is located from the first antenna at a distance of 12 millimeter. And we can simply create the second antenna from the first antenna just by copying the first antenna. It's very easy and very quick. So to do that, just go to the original patch center coordinate system, and then define a new coordinate system as the center of this whole system of the two antenna systems. And we can define a new variable for that, 0. Let's say distance is our new variable that denotes the distance between these two antennas. So let's select dist as the variable name. Fine. Okay. Now we can change the name of this coordinate system as center system. So this is the center of the two antenna system. All right. And now we can simply select all this structure and then duplicate and mirror. Select this center of this coordinate system, and from the keyboard press Z button, and then you can see the antenna is basically mirrored along the Z direction. Okay. Now we have these two antennas, and the newly defined components can be seen in this unassigned menu. We have to assign the ground plane, microstrip, and patch as the PEC. So I'm just selecting them and going to the boundary condition and select them as perfect E. And for the second wave port, we have to define another port for the second antenna. So I'm just renaming it to wave port 2. So this is our wave port 2. Let us hide the PEC cap 2. We can just select the second port and go to excitation and wave port in the same way like we defined in the first case. Just select the integration line from ground to microstrip line. And 50 ohm. All right. Now we have both the antennas. Now we need to define the breast phantom in between these two antennas. So for that, go to the original patch center coordinate system, and then create another coordinate system a little bit offset from the original one. So let's name this coordinate system as breast base, and this should be moved along z-axis, so it should be 0, and breast offset, let's define it as 1 millimeter. Okay. Now let us construct the breast phantom. What I'm going to do, I'm going to draw an arc on XZ plane. So change the working plane to XZ, and then select Draw Center Point Arc. Click on the center of this coordinate system and then press X button from the keyboard. That will restrict your movement along X-axis. Click anywhere on the X-axis holding the X button and then release the X button after clicking. Now you can see you can rotate it on the other side. Once you are on the other side, press the X button again from the keyboard and that will automatically snap on the negative X-axis. Now you can click anywhere and then release the X button and click on this point to end it. We can define the radius of this arc as the breast phantom radius, and the variable for the radius of the breast is breast rad. The value of this variable is 10 millimeter. All right, make sure your angle is 180 degree here. Now we have to join these two endpoints by a straight line. We have to parameterize this value. It is always good to parameterize because if you change the values later, you don't have to change everything manually. So breast rad. Okay. Now we have to unite these two polylines and then select, right click, go to edit, surface, cover lines. Now what I'm going to do, I'm going to sweep this 2D sheet along a semicircular path on the YZ plane. So change the working plane to YZ and draw an arc. So simply repeat the same process. Click on this center and this time press Y button from the keyboard. Right? That will restrict your movement along Y-axis. Now click anywhere on this axis and then release the Y button, and then you can go back to the other side and again press Y button just to snap on the positive Y-axis, and click here and release the Y button and just click here just to end it. So this is the path along which we are going to sweep this 2D sheet. This is the 2D sheet selected. This is the arc selected. Once you select the arc, it changes to pink color. Now go to sweep along path. Press OK. So this is the first layer of our breast phantom. If you recall our first part of the presentation, we showed a 3-layer model of our breast phantom. The first layer was the breast skin, and the second layer was the fat layer, and the third layer was the fibroglandular tissue layer. We are doing the same thing here in HFSS. This is the first layer. We have to create the second and the third layer as well. So we can name this layer as breast skin. We will define the material property later for all the layers at the same time. For the time being, we can change the color. First layer is complete. Now the second layer, I'm going to hide it because then I can work in a convenient way. I can see the things. So we are going to repeat the same process when designing this second layer. Draw an arc on the XZ plane. The dimension of this arc should be, the radius should be actually breast rad minus 0.5 millimeter. The reason of this minus 0.5 millimeter offset is the thickness of the first layer, the skin layer, is 0.5 millimeter. So that is why I'm using this 0.5 here. Again, connect these two endpoints by a straight line and parameterize this. It is basically breast rad minus 0.5 millimeter. We can simply copy and paste it here. Now simply join these two polylines, unite, and then right click, edit, surface cover lines. Now I'm going to draw another arc on the YZ plane, doing the same process like we did before. So select these two things together and sweep along path. So this is our second layer. We can rename it breast fat and change the color. If I show all the structures, you can see the first layer and the second layer as well. Now let's create the third layer. I'm going to hide both the layers first and repeat the same process. Draw an arc on XZ plane. The radius of this arc should be breast rad minus. This time we have to use 1 millimeter offset because the thickness of the first layer is 0.5, the thickness of the second layer is 0.5. So these two add up to 1 millimeter. Now, if I connect these two endpoints by straight line and then parameterize this value, negative breast rad minus 1 millimeter. Okay. In the same way, we have to join these two polylines and then select it, right click, go to edit, surface cover lines. All right. Now another arc on the YZ plane for the sweep. This time along the YZ plane. And select this shit and this polyline and go to sweep along path. So this is our third layer. Let me rename it breast fibro. And we can change the color as well. Now, if I show all the objects, then I can see the 3 layers together. But we have to do a little bit of geometrical manipulation here. We have to insert the layers into one another. Basically, all the layers are now overlapped. So let us select the first layer, the skin layer, and the second layer, fat layer, and go to subtract. Make sure your blank parts is the first layer, that is the skin layer, and the tool parts is breast fat, that is the second layer. And you must enable this. Okay. Now select the second layer, that is the fat layer, and the third layer, the fiber layer. And again, go to subtract. Make sure your blank part is basically the second layer and the tool part is the third layer. And you must enable this. Okay. Now you can see a very nice representation of the 3 layers. So if I make the first layer transparent, then maybe you can see a little bit clearly. Don't worry about the stripes. These are basically because of HFSS graphics, maybe. But these stripes don't matter at all. Don't worry about them. And the second layer is fat layer, if I make it transparent as well. And the third layer, Now you can see all the three layers inside of one another, right? Now, if you recall, we used a table. That table was basically the table of permittivity and the tangent loss of different layers of the breast phantom at 33 gigahertz. So I'm going to define the material property right now. We have all the three layers. So let's define the first layer material property, breast skin. Right click and then go to assign material and select add material. Let's name it breast skin. The permittivity of this breast skin layer was 17.7 and the dielectric loss tangent was 0.93 at 33 gigahertz. Okay, so this is the first layer. Now let's select the second layer, the fat layer. Assign material, add material, breast fat. The permittivity was 3.4 and the dielectric loss tangent is 0.16 at 33 gigahertz. In the third layer, assign material, add material, breast fibro. The permittivity was 16 and the tangent loss was 0.94. Frequency is 33 gigahertz. So we have breast skin layer, breast fat layer, and the fiber layer. Three layers, right? And now let's create the areola here. Let's create another coordinate system. Let me define it as 0, 0, areola distance. Let me define it as breast rad minus 0.5 millimeter. Now again, change the coordinate system to XZ and draw an arc, basically. And now, let me define the dimension of areola. The radius of this arc should be the radius of areola. Areola rad let me define it as 1 millimeter. And let's connect these two endpoints by a straight line. This is basically areola rad, areola rad. Now let us join this polyline 10 and 11. And now let us create another arc on the YZ plane. So change to YZ and draw another arc on YZ plane. Actually, we have to create the sheet out of this polyline 11 actually. So go to edit, surface, cover lines. So simply select these two, this sheet and the arc together, and sweep along path. So this is our areola. We can rename it areola material, you can use breast skin material. You can change the color as well. And basically you can join breast skin and areola together. Just simply unite them together. Okay, now we have to create the tumor cell inside the breast. In order to define the location, or in order to parameterize the location of the tumor cell, we need to define 3 new parameters, all right, to describe the X, Y, and Z coordinate of the tumor location. So for that, go back to the global coordinate system again. Just simply double click on this coordinate system. And now let us create another coordinate system for the tumor location. Just go to anywhere on the inside of the breast. Click anywhere. Okay, now this is the newly created coordinate system. Let us name it as tumor location, CS. Now I'm going to define 2 new parameters for the tumor coordinates. For the X coordinate TX, Y coordinate TY, Z coordinate TZ. And the value, let me define as 0 millimeter first. And for the Y, 0 millimeter. For the Z, maybe 5 millimeter. Now we have to create tumor here. Simply select this sphere and click on this center point and draw a sphere. So this is our tumor. We can rename it to tumor. The material, recall the permittivity and the tangent loss for the tumor should be defined. So let us create a new material again for the tumor. Let's name it tumor. The material was, the permittivity was 18. Tangent loss was 1.05. Measured frequency should be 33 gig. Let us change the color to black. And the radius of the tumor is defined by a variable tumor rad. Let me define as 2 millimeter. So if I simply increase the transparency level, you can see the tumor inside. So we have designed everything, but we have to also design the radiation boundary now. So for that, select center system, this coordinate system, go to rectangular box, and now we can define the dimensions of this box. Let me define as -12, -12, -8. So this should be 24, 24, and let me define as 16. And let me make it quite transparent. Now we can see the structures inside of this radiation boundary. This is vacuum, so we must assign radiation boundary for this radiation box. Go to boundary and assign radiation. And these are the perfect E conductors. Wave port 1 and wave port 2. So this is the whole design. And another interesting fact is that since we have parameterized the location of the tumor, you can actually vary the location of the tumor by just changing the coordinate values. For example, TX, you can see the tumor has moved, and TY ty is equal to 2, it will move again. So simply, this is the power of parameterization. You can simply change the coordinate later, and you can just simply change the location and do a different simulation sweep and compare the S2-1 plot for that particular location of the tumor. For the time being, I'm just using Tx and Ty as 0, 0, and the Tz is equal to 5 millimeter. All right. Anyway, now let's go back to the simulation setup. We have to define analysis, right click, go to solution setup, advanced. The operating frequency for this antenna is basically 33 gigahertz. So I'm going to use a little bit more number of passes just to make sure the mesh is fine. There is a trade-off basically. If you increase the number of passes, it will take a longer amount of time to simulate the structure, and because in each pass it will refine the mesh and calculate the maximum delta and satisfy the criteria. And yeah, that will take a lot of time and computing resources like RAM and processing power. So make sure you do not give a large number here. Maybe 10 is fine, and the maximum delta is 0.02 is also fine. If you increase this number, the simulation would be less time consuming, but the accuracy would be a little bit reduced. For example, if I use 0.1, it would be a little bit quicker than using 0.02. But anyway, I'm using 0.02 for this simulation. And since my system is operating at 33 gigahertz, so I'm going to sweep from 32 to 34 with frequency points. 20 is enough, I think. And make sure you enable this save fields. And the sweep type is discrete. Again, if you go to Optimetrics and right click and add parametric, then basically you can add parametric simulation here. For example, if you add the tumor radius as a parameter sweep, and you want to vary the size of the tumor from 1 to 3 millimeter, and the step is 0.5 millimeter, then the sweep will be added. The simulation will be performed 5 times for different sizes of these tumors. And yes, you can also add another parameter. For example, for the location, Tx, you can add, for example, from 1 to 5, this step of 1. Now you can check the table. You have total 25 simulations. So all the possible combinations between these two parameters basically are being shown here. So it will take a lot of amount of time. So make sure you do not add unnecessary parameters here just to check the sweep. Make sure you utilize your resources in a wise manner in order to avoid all possible combinations of these two parameters. You can basically sync them, and that would reduce to only 5 simulations. So this will take a little bit less time compared to the previous one, which had 25 simulations. Okay. Now you can check your simulation is ready or not. Just press validate, and all the tick marks are actually green. That means you are good to go. Press analyze all, and the simulation will start. You can check the progress here. And once the simulation is done, basically you can access the S2-1 parameter from this rectangular plot. Here you can select S2-1 in dB scale, press new report. Because the simulation is running, that's why the S2-1 plot is empty. Once the simulation will be complete, then you can see the plot. Here, S2-1 plot. So I hope that this video has been very useful for you to know how to design this entire system. And so if you find this video useful, press like and subscribe to our YouTube channel. And if you have any question, you can join our Facebook group called Antenna Lab and post your question there. Thank you very much for watching this tutorial.